Open channel flow is the movement of water with a free surface exposed to the atmosphere, such as in rivers and canals. In uniform flow, the water depth and velocity remain constant. A hydraulic jump occurs when fast-moving water suddenly changes into slow-moving water, causing the water level to rise and energy to be dissipated. Understanding these hydraulic parameters is important for designing safe and efficient water channels and preventing erosion.
Objective of this experiment are to observe the flow pattern and changes in water depth before and after a hydraulic jump. The experiment also compares the upstream and downstream flow depth to a better understanding of hydraulic jump process. In addition, it investigates the characteristic of the transition from supercritical to subcritical flow. Besides, it calculates the energy dissipation and power loss during the principle of specific energy. In civil engineering, high-velocity water that released from structures such as sluice gates carry high kinetic energy that can cause severe erosion and damage to riverbed and hydraulic structure. A hydraulic jump acts as a natural energy dissipator, reducing flow velocity and protecting downstream infrastructure. Therefore, this experiment investigates the relationship between the hydraulic parameters under different flow rates to evaluate energy dissipation and support the safe, stable, and sustainability designs of hydraulic structure.
The first step to conduct the experiment is to measure the width of the rectangular open channel by using the vernier caliper.
As we can see, the width of the rectangular open channel is 7.8 cm. Next, we measure the height of the sluice gate. After that, adjust the sluice gate in a correct state. Make sure the sluice gate is locked afterwards.
Next, we switch on the hydraulic bench and then we open the valve to control the flow rate. And then place the tailgate at the end of the rectangular open channel.
After the water is level, we measure the height of Y. After that, the height of Y1 is measured before the water jump. After that, the height of Y2 is also measured after the water jump. After everything is measured, we record the flow rate and record the time.
Based on our experiment, we get the result of height of tailgate, height of sluice gate, volume, time, Y1, and Y2. The first step is we need to calculate the flow rate. Q equals to V volume divided by T time. Next, we need to calculate the velocity V1 and V2. We use the formula of Q equals to A area multiplied by V velocity. Same as Q equals to PT V. Next, we need to find a Froude number FR1 and FR2. We use the formula of FR equals to V velocity divided by sec G gravity multiplied D depth. Next, we need to calculate the head loss. We use the formula of open bracket D2 minus D1 plus bracket power of 3 divided by 4D1 multiplied D2. Lastly, we need to calculate the power loss. We use the formula of P equals to rho 1000 G gravity 9.81 multiply Q multiply HL, which is head loss.
We are now focusing on the discussion part. We have to submit. Right now, let's discuss on what our data means. We take Q as 0.00052 meter cube per second. We measured and can conclude that V1 is larger than V2. This confirmed that velocity dropped after the jump because energy was lost from the upstream flow. We also calculated Froude number 1 to be 1.65, which is greater than 1. Means the flow before the jump was supercritical, fast and shallow. However, FR2 yields 0.88, which is less than 1. This indicates the flow became supercritical after the jump, slower and stable. The energy that lost due to turbulence is calculated as 0.0025 meters. This HL value tells us how much energy would erode the channel bed. Power dissipation is 0.002E. Overall, as Q increases, V and FR also increase, resulting in a stronger hydraulic jump with higher head loss and power dissipation. Next, our experiment connects directly to SDG9. We apply the concept to structures like dams, spillways, and weirs. In real world, uncontrolled supercritical flow in these structures can cause erosion and severe damage. By understanding this problem, engineer can design scaling basins to control and dissipate the massive jump's energy. This could reduce maintenance costs and make the structure resilient and sustainable, which support SDG9. One infrequently encountered issue is the unpredictable location of the hydraulic jump under high Froude number conditions. The jump can suddenly move downstream, causing random bed erosion and reducing the effectiveness of energy dissipation. To solve this, we propose a mini scaling basin with zigzag baffle blocks. The staggered arrangement forces the flow to change direction repeatedly, increasing turbulence and dissipating energy within a shorter distance, which stabilizes the hydraulic jump and protects the channel bed.
In conclusion, the experiment successfully achieved all of its objectives. The results show that the hydraulic jump changed the flow from fast, shallow supercritical flow to slower, deeper subcritical flow. This was confirmed by the increase in downstream water depth and the calculated Froude numbers. The experiment also showed head loss and power loss, proving that energy was dissipated during the hydraulic jump. Overall, the results agreed with hydraulic jump theory and demonstrated its importance in reducing flow energy and protecting hydraulic structures from erosion and damage.